Stop scrolling. Take a breath. This might shake your confidence a little. You think you understand quantum physics. You have heard the phrases, parallel universes, particles in two places at once, the observer effect. It sounds strange but familiar. You nod when someone mentions it. You watch short videos about it. You feel like you get the basic idea, but the truth is simple and uncomfortable. You don't actually understand it, and that is not an insult. It is a fact that even the greatest minds in history struggled with. Quantum physics did not just confuse students, it divided legends. Albert Einstein, one of the smartest humans who ever lived, rejected parts of it. He spent years trying to prove it was incomplete. He believed the universe had to be logical and deterministic. He hated the idea that reality at its core runs on probability. He once argued that the universe does not play dice, yet experiment after experiment showed that nature does not follow his expectations. Then there was Erwin Schrödinger. He helped build quantum theory, yet he was so disturbed by its meaning that he created a thought experiment about a cat that is both alive and dead. Most people know the cat story. Few know that Schrödinger invented it to show how absurd the theory sounded when applied to the real world. He was not celebrating quantum physics, he was exposing how uncomfortable it really is. And then came Werner Heisenberg, who mathematically proved that there is a fundamental limit to what we can know, not because our tools are weak, not because we are careless, but because reality itself does not allow complete precision. The more accurately you measure a particle's position, the less accurately you can know its momentum. This is not a technology problem. It is built into the structure of existence. And then there was Niels Bohr, who pushed things even further. He argued that asking what a particle is doing before we measure it might be meaningless. According to his view, reality at the quantum level does not settle into a definite state until observation happens. That idea is not just technical. It is philosophical dynamite because it hints that observation plays a role in shaping reality itself. These men were not internet theorists. They were founders of modern physics. They built the equations that power today's technology, yet they could not agree on what those equations actually mean. They argued for decades. Letters were exchanged. Debates grew intense. Friendships were tested. At one famous conference in the early 20th century, Einstein and Bohr challenged each other again and again over the nature of reality. Einstein designed clever thought experiments to prove quantum mechanics was flawed. Bohr found ways to defend it each time. This was not just science. It was a battle over the nature of truth. And here is the lesser-known part. Even today, more than 100 years later, there is still no single agreed explanation of what quantum physics says about reality. The math works perfectly. It predicts outcomes with shocking accuracy. It allows us to build lasers, transistors, and the devices that run the modern world. But when you ask what is really happening behind the equations, the answers split into different interpretations. Some physicists believe in many worlds. Others believe in hidden variables. Others accept that probability is the final layer of reality. The equations stay the same. The stories change. That should make you pause. Because if the creators of quantum theory could not agree on what it means, what makes anyone think a few simplified sentences on social media capture the truth? In this video, you will learn why quantum physics feels understandable on the surface, but collapses under deeper questioning. You will see how your brain is wired for a classical world of solid objects and clear causes, and why that wiring fails at the atomic scale. You will understand the measurement problem, and why it remains one of the biggest open questions in science. You will discover why removing the math from quantum mechanics removes its real meaning. And you will see how even today, inside advanced research centers like CERN, scientists are still testing the boundaries of what this theory truly implies. By the end, you will not just know more facts. You will understand why true understanding of quantum physics is so rare. You will see the gap between catchy explanations and the deep, unsettling truth, and you will realize that the mystery is not a weakness of science. It is a reflection of how strange reality really is. Stay with me until the end, because the final part will reveal the real reason your mind resists quantum physics, and why that resistance might tell us more about human nature than about atoms. Welcome to the channel. If you are curious about the universe, reality, and the limits of human knowledge, you are in the right place. Subscribe now, and let's begin this journey into the deepest layer of existence. Confidence comes easily when the story sounds simple. Modern pop science has mastered the art of turning deep theories into short, powerful phrases. A complex equation becomes a colorful animation. 100 pages of mathematics become a 3-minute explanation. The language feels friendly. It feels empowering. It feels clear. Words like energy, vibration, manifestation, and parallel timelines move quickly across screens. They are repeated so often that they start to feel scientific. They borrow the tone of physics. They borrow the mystery. And soon the mystery turns into a feeling of understanding. But repeating vocabulary is not the same as grasping structure. Hearing that everything is energy does not mean you understand what a wave function is. Saying that reality is vibration does not mean you understand probability amplitudes. Talking about parallel timelines does not mean you understand the mathematics behind superposition. Pop science removes the difficulty. It removes the symbols. It removes the tension between equations and intuition. And without that tension, the sharp edges disappear. What remains is a smooth story that fits comfortably inside everyday thinking. That comfort creates an illusion. It creates the feeling that the strange has been tamed. Social media accelerates this illusion. Short clips reward speed. Algorithms reward bold claims. The more dramatic the statement, the more attention it gains. Quantum physics becomes a playground for simplified ideas. The uncertainty principle becomes a slogan. Superposition becomes a mystical state of being. Entanglement becomes proof that thoughts can influence distant reality. The vocabulary stays scientific, but the meaning shifts. The hard mathematics is replaced by emotional appeal. The original theory is built on linear algebra, complex numbers, Hilbert spaces, operators acting on wave functions. None of that survives the journey into viral content. The cold structure is replaced by warmth and excitement, and that warmth makes people feel informed. But quantum physics itself is not warm. It does not try to comfort. It does not try to inspire. It does not promise personal transformation. It is mathematical. It is exact. It is indifferent to human hopes. Its predictions come from equations that must be solved step by step. If you remove the equations, you remove the engine. What remains is decoration. Understanding words is easy. Understanding formalism is hard. And because most people never see the formalism, they assume the words are enough. They assume that if they can explain an idea in a sentence, they understand it. But in quantum mechanics, the sentence is only the shadow of the structure. The real meaning lives inside symbols. When physicists talk about a particle being in two states at once, they are not imagining a tiny object splitting in space. They are describing a state vector in a mathematical space. When they speak of probability, they are not guessing. They are calculating exact amplitudes whose squares give measurable outcomes. The gap between everyday language and mathematical description is enormous. That gap is where the illusion grows. It grows because the brain prefers stories over equations. It prefers images over abstractions. It prefers metaphors over matrices. And that preference makes sense when you look at how the brain evolved. The human brain was not designed in a laboratory. It was shaped by survival. It learned to track movement in tall grass. It learned to judge distance. It learned to predict the path of a thrown spear. It learned to separate friend from enemy. These skills rely on classical logic. An object is either here or there. A sound either signals danger or it does not. A fruit is either ripe or rotten. Clear categories improve survival. Ambiguity can be fatal. So the brain developed shortcuts. It developed intuition that works well in the visible world. That intuition assumes continuity. It assumes solidity. It assumes cause and effect in a straight line. Throw a stone, and it travels in a predictable arc. Drop a cup, and it falls. The world of medium-sized objects behaves in stable ways. Classical physics describes that world beautifully, but atoms do not live in that world of medium-sized certainty. At the quantum scale, particles do not behave like tiny stones. They follow mathematical rules that do not align with everyday categories. Classical logic says a thing cannot be in two places at once. Quantum mechanics describes states where position is not fixed until measurement. Classical logic says a system has definite properties, whether we look or not. Quantum theory suggests that some properties do not settle into definite values until interaction occurs. This clashes with instinct. Instinct whispers that reality must be solid beneath the surface. Quantum mechanics answers with probabilities. This clash creates discomfort, and when discomfort appears, the brain searches for relief. Simplified explanations provide that relief. They allow intuition to remain in control. Instead of wrestling with complex numbers, the mind replaces them with images. A particle becomes a tiny sphere that flickers between positions. A wave becomes a literal ripple in space. But these images are approximations. They are teaching tools. They are not the theory itself. The theory itself is abstract. It lives in equations that predict results without offering a simple picture. That is why even trained physicists speak carefully when describing what is happening. They separate calculation from interpretation, and interpretation is where disagreement begins. The central confusion emerges most clearly in the measurement problem. Experiments show that particles display wave-like behavior. When not measured in a way that determines a specific property, they interfere with themselves. They create patterns that look like ripples overlapping. Yet when a measurement is made that forces a definite outcome, the behavior changes, the pattern disappears, a specific result appears. This shift between wave-like and particle-like behavior is not just a visual trick, it is built into the mathematics of the theory. The wave function evolves smoothly according to one equation, but measurement introduces a different rule, often described as collapse. The smooth evolution suddenly becomes a single outcome, and here the questions begin. What exactly counts as a measurement? Is it any interaction with the environment? Is it a device recording information? Is it a conscious observer becoming aware of the result? Different interpretations answer differently. Some say collapse is only apparent, that the system becomes entangled with its surroundings, and the appearance of collapse emerges from that entanglement. Others suggest that collapse is a real physical process, not yet fully understood. A few have proposed that consciousness plays a role, though this remains controversial and not widely accepted in mainstream physics. The disagreement shows that while the equations predict probabilities with astonishing accuracy, the story behind those probabilities remains unsettled. When people first hear that observing a particle changes its behavior, they often imagine a human eye forcing reality to shift. That image spreads quickly because it feels dramatic, it feels powerful, but in laboratory practice, measurement usually means interaction with a device. A detector clicks, a screen lights up, a photographic plate records a mark. The mathematics does not require a human to stare at the particle. It requires interaction that distinguishes outcomes. Yet even this clarification does not erase the deeper issue. Why should interaction produce a single definite result at all if the underlying equation describes a spread of possibilities? This is the heart of the measurement problem. It is not solved by catchy phrases. It is not resolved by appealing to mystery. It sits at the foundation of the theory. Even experts debate its meaning. Some adopt the Copenhagen interpretation, often associated with Niels Bohr, which emphasizes the role of classical measuring devices and accepts that quantum properties are not definite until measured. Others prefer the many worlds interpretation, proposed by Hugh Everett, where all possible outcomes occur in branching universes and no collapse happens. Still others explore pilot wave theories, objective collapse models, or relational interpretations. Each approach preserves the predictive success of the equations. Each tells a different story about reality. For someone outside the field, hearing that respected physicists support incompatible interpretations can feel unsettling. It challenges the assumption that science always delivers a single clear picture, but the predictive core of quantum mechanics remains unshaken. The confusion lies not in experimental results, but in the meaning assigned to them. This distinction is subtle. It requires separating calculation from narrative, and that separation is difficult for a mind trained to seek unified stories. The brain prefers a single consistent image. Quantum mechanics offers a toolbox of formalisms that work perfectly while leaving room for multiple conceptual frameworks. That gap invites misunderstanding. It invites oversimplification, and oversimplification feeds the illusion of understanding. People hear that particles behave like waves and picture water. They hear that measurement collapses possibilities and picture a dramatic snap. These pictures are not entirely wrong, but they are incomplete. They are scaffolding around a structure made of mathematics. Without engaging with the structure, the scaffolding becomes the whole building. The mind feels satisfied. It believes it understands, but when pressed with deeper questions, the clarity fades. What exactly is a wave function? In what space does it exist? How does probability emerge from complex amplitudes? Why do interference patterns appear? How does decoherence relate to classical outcomes? These questions demand patience. They demand formal training. They demand acceptance that intuition will fail. And that is where many people stop. They prefer the simplified version. They prefer the illusion because the illusion preserves comfort. It keeps the world aligned with familiar logic. The real theory does not offer that comfort. It asks the mind to accept that at the smallest scales, reality does not behave like everyday objects. It asks the mind to operate without a clear picture. It asks for trust in equations that resist visualization. That demand feels unnatural. It feels unfair, but it reflects the limits of cognition shaped by evolution for survival, not for decoding the fabric of the universe. And as long as those limits remain, the illusion of understanding will remain tempting, wrapping complex mathematics in simple words, while the deeper questions continue to challenge even those who dedicate their lives to studying them. Here is another uncomfortable truth that rarely goes viral. Quantum physics is not explained in English. It is explained in equations. The real theory does not live inside sentences. It lives inside symbols. It lives inside matrices, operators, integrals, complex numbers, and abstract spaces that cannot be pictured in the mind. When physicists talk to each other, they do not rely on metaphors about cats or parallel worlds. They write down wave functions. They calculate amplitudes. They apply linear algebra to Hilbert spaces. That is the language of the theory. And once you remove that language, once you strip away the equations and replace them with simple words, you are no longer holding the theory itself. You are holding a translation, and every translation loses detail. In quantum mechanics, the detail is everything. A small change in a sign inside an equation can completely change a prediction. A missing factor of I, the imaginary unit, can destroy the entire structure. This is not poetry, it is precision. Most people are comfortable with metaphors. A metaphor feels like understanding because it connects the unknown to the known. A wave function becomes a ripple. A probability amplitude becomes a chance. Superposition becomes a coin spinning in the air. These images help at the beginning, but they hide the depth. A wave function is not a water wave. It does not move through space in a simple physical way. It is a mathematical object that contains all possible information about a system. It evolves according to the Schrödinger equation, which tells you how probabilities change over time. But that equation is not intuitive. It does not describe a tiny ball rolling on a surface. It describes how complex numbers rotate in an abstract space. Without learning that mathematics, you cannot truly see what the theory is saying. You can only hear an echo of it. Probability amplitudes are not the same as everyday probabilities. They can interfere. They can cancel each other out. Two possibilities can combine and reduce the chance of an event happening, even though each one alone would increase it. That behavior does not exist in simple classical probability. It exists because amplitudes are complex numbers that add before being squared. This detail is often skipped in popular explanations, yet it is the heart of quantum interference. Remove that, and the mystery turns into a vague story about particles acting weird. With the math, the weirdness becomes structured, it becomes calculable, it becomes exact. Without the math, you are only holding shadows cast by something far more intricate. This is why many physicists quietly admit that understanding quantum mechanics means being able to work with the equations, not just talk about them. There is a famous line often repeated in physics circles, commonly linked to Richard Feynman, who once suggested that if you think you understand quantum mechanics, you probably do not. The point of that statement is not to insult curiosity, it is to warn against overconfidence. Even those who dedicate their lives to the subject admit that the deeper meaning remains slippery. The equations predict outcomes with stunning accuracy. They tell us the energy levels of atoms. They allow us to design semiconductors. They explain chemical bonds. They guide the creation of technologies that define modern life. In that sense, the theory works perfectly, but when you ask why it works, or what reality looks like underneath those equations, the clarity fades. Physicists can calculate the probability that a particle will appear in a certain place. They can measure it in experiments and confirm the prediction to many decimal places. Yet when asked what the particle was doing before the measurement, answers begin to differ. This is where interpretations enter. The Copenhagen interpretation, often associated with Niels Bohr, suggests that quantum systems do not have definite properties until measured. The act of measurement forces a specific outcome from a range of possibilities. In this view, the wave function represents knowledge or information about the system, not a physical object in space. Then there is the many worlds interpretation proposed by Hugh Everett. In this framework, the wave function never collapses. Every possible outcome actually occurs, but in separate branches of reality. The universe constantly splits into multiple versions, each containing a different result. The mathematics remains the same, only the story changes. Another approach is the pilot wave theory, developed by David Bohr. This interpretation introduces hidden variables that guide particles along definite paths, restoring a form of determinism beneath the surface randomness. Again, the equations reproduce the same experimental predictions as standard quantum mechanics. The surface remains identical. The underlying explanation shifts. These interpretations disagree deeply about what is real, yet they all use the same formalism. They all match the same data. There is no final experiment that clearly selects one interpretation over the others. That fact alone should slow down anyone who claims complete understanding. When a theory allows multiple incompatible stories while preserving identical predictions, it reveals a gap between calculation and comprehension. The gap is not a failure. It is a sign that the mathematical structure might be deeper than our current conceptual tools. And this brings us to the deeper reason most people do not understand quantum physics. It is not about intelligence. It is not about effort. It is about expectation. Human minds crave logical continuity. We want causes to produce clear effects. We want events to unfold in a chain we can follow. Classical physics provides that comfort. If you know the position and velocity of a planet, you can predict its path. The universe feels like a machine. Quantum mechanics breaks that image. It replaces certainty with probability. Even with perfect knowledge of the wave function, you can only calculate the likelihood of outcomes. You cannot predict a single specific result with certainty. That randomness is not due to ignorance. It is built into the theory. You want solid ground. Quantum physics gives clouds. You want objects with definite properties. Quantum physics describes states that exist as combinations of possibilities. The universe at its smallest scale is not made of tiny solid things in the way we imagine. It is described by mathematical structures that encode potential outcomes. When measurement occurs, one possibility becomes actual. Before that, the system exists in a superposition. That word is often repeated, but its meaning is precise. It means the system is described by a linear combination of states. Each state contributes to the overall wave function. Only when an interaction forces a definite result does one outcome appear. This idea challenges the desire for fixed reality. It suggests that potential is as fundamental as actuality. That suggestion feels unstable. It feels like standing on shifting ground. Yet experiment after experiment supports the predictions. Inside large research facilities like CERN, scientists continue to test quantum theory under extreme conditions. They collide particles at enormous energies. They analyze decay patterns. They search for tiny deviations from predicted behavior. So far, the core principles remain intact. The probabilistic nature of reality persists. The mathematics continues to work, but foundational questions remain open. How does classical reality emerge from quantum rules? Why do we experience definite outcomes instead of superpositions? Is there a deeper layer beneath the wave function? These questions are not signs of weakness. They are signs of active exploration. Not understanding quantum physics does not mean you lack intelligence. It means you are confronting the edge of current human knowledge. It means you are stepping into a domain where intuition breaks and mathematical scientists themselves admit uncertainty about interpretation. They debate, they publish papers, they propose new models, they test boundaries. The lack of a final philosophical agreement does not reduce the power of the theory. It highlights the difference between predicting and explaining, and that difference is uncomfortable. It reminds us that knowledge can be precise without being complete. We are still learning, still refining, still questioning the foundations of a framework that has never failed experimentally, yet continues to resist simple explanation. That tension between success and mystery defines quantum physics. It does not collapse into a neat summary. It stretches forward, inviting deeper inquiry while resisting final closure. So we return to where we started. You don't understand quantum physics, not completely, not in the way you understand gravity or motion or fire. But here is the truth that should both unsettle you and comfort you at the same time. Neither does anyone else. Not fully, not in the deepest sense. The equations work. The predictions match experiments with shocking precision. The technology built on top of it powers your entire modern world. Yet when we ask what is really happening behind those equations, silence still fills the gaps. Debate continues. Interpretations compete. Questions remain open. And maybe that is not a weakness of science. Maybe that is the lesson. The universe is under no obligation to make sense to your brain. Your brain was built to survive on a small planet, at a medium size, moving at slow speeds. It was not built to picture probability waves in abstract spaces. It was not built to feel comfortable with particles that exist as possibilities. It demands clarity. Reality offers mathematics. It demands certainty. Reality offers probabilities. It demands solid ground. Reality offers clouds. And that clash between expectation and truth is what makes quantum physics feel so disturbing. It shakes the idea that the world must behave in a way that feels logical to us. It forces humility. It reminds us that intelligence does not guarantee intuition, that the deepest layers of existence may never fit neatly into human imagination, and that is what makes it terrifying, because it means there are limits to how far comfort can take us. But it is also what makes it beautiful, because it means the universe is deeper than we thought, stranger than we assumed, more layered than our common sense allows. It means there is still mystery at the foundation of reality, still room for discovery, still room for wonder. The fact that we can even write equations that describe such a strange world is already extraordinary. The fact that we can test them, challenge them, and keep refining our understanding is even more extraordinary. So no, you don't understand quantum physics completely, but you are not alone. None of us stand above the mystery. We stand inside it. If this video challenged the way you think, if it made you question what you thought you knew, then this is just the beginning. There is so much more to explore about reality, science, and the limits of human knowledge. Like this video, If you enjoyed it, share it with someone who thinks they understand quantum physics, and subscribe to the channel for more deep dives into the ideas that reshape the way we see the universe. The mystery is not going away, and neither are we.